So welcome to a lecture on robot mapping. This is the second last lecture, or let's say the second last day. Today we're going to talk about two topics. First one is robust least square, so how to handle outliers, and we'll see soon what outlier means. And the second part will be on stochastic gradient descent for SLAM, which also is, let's say, robust to outlier in some sense, and we'll see it later on. So, least squares, we've seen that as a least squares, we mean that we want to minimize the sum of the squared error, where error is the discrepancies between the predicted measurement and the actual measurement. We also have seen that this is equivalent to maximum likelihood estimation in case all our measurements are Gaussian measurements, or random variable whose error is distributed according to a Gaussian random variable. The problem in this case is, first of all, we are only considering Gaussians in the sense of we're only considering measurements which are unimodal, meaning that we assume that our measurement is correct and there is just a bit of deviation around the value that we get from our sensor. But we're not considering what's called multi-hypothesis or multimodal measurements, where we can say something happened and that can be either A or B with some noise around. Okay? One typical example could be slippage. Imagine that the robot is moving on a very slippery terrain. You could have two potential outcomes. One is that the robot performed the actions as usual, so you will get one hypothesis, the robot moving forward and there's a bit of noise. Or you can have the second hypothesis where the robot is slipping, so it's just staying where it is. And it's not possible to model those two as one big action because actually there are two different outcomes. Okay? And that's where using only one single mode or one Gaussian distribution is not enough, it's not powerful enough to model that. And the second thing is that they are sensitive to outliers. This is still related to the concept of using a Gaussian error, because the Gaussian assumes that what you're getting is a true measurement and is only affected by some noise, but it doesn't consider extreme cases, or is not able to model extreme cases of something being very, very far away from the mean. And we'll see what this means and what implies that. So the problem in real world is that when we build this graph, so when we build this measurement between nodes, we are actually doing some decision step from real data. So we are trying to get sensor data and trying to make a decision if those sensor data belongs to the same place or not. And we might have multiple hypotheses. So like there might be environments who are ambiguous. Imagine imagine a building in 3D where each floor looks the same, or like a hospital where you have those corridors and different rooms that all look the same. So it's hard to say these two places, this place is exactly this one, but you can more likely say this place might be A, B, C, or D. No, and but other problems are clutter scenes where you have a lot of things around, so it's very hard to understand if these two places are actually the same or not. And in a very specific case, when you use GPS sensors, you have what is called multipath. So basically the signal from the GPS jumps around buildings, so you have one measurement, this direct measurement, and the other one that does the jumping around, and you want to discern which is which. So this is to say that when we do in the front end, so in the part that builds the graph and makes data association decision, not always, nothing is perfect, and while the optimization step actually requires that everything is perfect, that these measurements are true. And now the question is how we can handle a bit of mistakes from the data association layer and put some additional steps into the optimization part that is able to handle small mistakes on the association layer. Here we can see, for instance, example of ambiguity. Imagine that this is the 3D world, that's the robot here, and everything looks the same. So once the robot is here and looks at these 4 blocks, actually can be either here, here, and there, or it can be oriented in a different way. And if you now look at how the cost function looks like, so if you just go all around the all potential places where the robot can be and you just evaluate the error, you get something which is very hilly. There's a lot of different hills, so each of these is one different hypothesis or local minima, and you can see that you can be either here, here, there, or no. And getting to the exact global optimum, it's very hard if you start somewhere which is not a good place. So we want to be able to handle this kind of measurements, this kind of ambiguity within the optimization framework. In reality, you can also have the same situations. Imagine this is now a data set, that's an indoor environment, that's the Intel environment. If you now look at how the environment looks like from this area or this area, you can see that the only thing that the robot is looking at are a couple of parallel walls and some perpendicular walls. The red one is what the robot is looking right now. It's some measurement on this wall, some measurement on this wall, some measurement on that. And they all can look the same as this one, no? Because you get that this wall can be matched by this wall, or it can also be similar to situations like here where there is this matching with this matching, or something like here where there is this matching with this matching. So that's to say that the place up here can look like a place very far away, and that's because indoor environments especially have a kind of repetitive patterns that repeats themselves all over the environment. Yes?
So the red part is the observation and the blue parts are the maps, right?
Yes, so here basically we are trying to match the current laser data to different places in the environment, and the red one is the current laser measurement, and the blue one are the measurements taken at the other location, so the one which are up here or down there. Okay, and the red one is actually seen from here, no? So that's how that's what we are comparing it. So that's the current pose of the robot. Okay. Now, what happens if we include some of these wrong measurements? So let's assume at some point we have to build this graph, and you say, okay, let's say this shoe looks the same, like this one up here. Let's compute the measurement, let's include it in the graph, let's take it into our optimization phase. This means we are including an edge between these two nodes. What will happen is that according to how many of these edges we include, our final results will collapse and together, because so what you're telling to the optimizer is like this place and this place should be in the same part. So there is like a spring pulling these two places together. And then there is a lot of other springs that are pulling them apart. But since, depending on how many springs are here and how many springs are there might be this kind of collapse in together, okay? But there is no way of, by just using the Gauss-Newton algorithm or by just minimizing or solving a least squares problem, there is no way of cutting this out. There will always be an influence of this one in the standard formulation. And what we are explaining today is how can we handle this kind of cases and how can we make sure that in this kind of situations, those errors or those measurements can be eliminated, okay? So we're going to go through two different steps, which are different approaches in the literature, and then at the end, trying to put all of them under one umbrella. And let's now try to look at different cases that we have seen there can be ambiguity. So how can we incorporate all of them into SLAM? So any idea? So we know that all of this can basically ends up in multiple hypotheses. No, like places that look identical, you can have that two places might be the same, so you can have multiple hypotheses. How do you think we can model them? Any idea? So we have seen that the normal way of modeling data association in terms of measurements, we are saying we are considering relative measurements. So there is one node 1 and node 2, okay? And those two nodes are related by a measurement, okay? Now, if we're saying that there is a third node here, and all of these are like 3 different places. Now, we can include both of them and saying the first one, this measurement can be associated with this one, or it can be associated with this other place. So we have connection between those two. But we also want to include an option here that somehow says, but it can also be not true, or it can also be not true, right? Because we want to consider the true hypothesis. Either is the same place or is not. Or we can decide, if you look at this from only the node 1 point of view, you can say it can be like somewhere around here, or it can be somewhere around here, no? So we are including multiple hypotheses there. And each of these mode is like one Gaussian, and if we take a distribution which has different modes, we can see that this is it's called a mixture of Gaussian distribution. So there are different hypotheses, okay? Now, it's not so trivial to go from a graph to this, because there is a lot of, for instance, you can include mutual exclusion and all these things. So, but if you look at one single measurement and try to give multiple interpretation of this measurement, this is a valid tool. And this can easily address the problem of the slippage that I see before, because you say there is a temporal relation between the robot at times t and times t plus 1, and this temporal relation can be caused by 2 phenomena, no? By the slippage phenomena and by the motion phenomena. Okay? Is it clear? Do you have any question? Okay. So, and the way to express it mathematically, we said, this is the classic way we did before, no? We had a measurement Z, the state space X, and we said that this is modeled as a Gaussian distribution, no? So the E here is the error, and by this we mean the difference between the predicted measurement and the real measurement. We have our information matrix and the error again, no? So that's how we have done it so far. If you want to include multiple hypotheses, or if you want to see them as a mixture of Gaussian, we have a sum of a lot of this Gaussian distribution. Okay, so we have this exponential here, the bell curve, the one that you can see up there. There is a weight that modulates how likely one mode is with respect to another, and then we sum them up. Okay? So that's how we do a mixture of Gaussians. That's a mathematical way of depicting a distribution that looks like that. Okay? Now, whenever we do the error minimization, so whatever we do, we transform this maximum likelihood problem into a optimization problem, we often take the negative log likelihood. Okay? We do this because the least squares formulation requires a sum of quadratic terms, and in the likelihood formulation, we have a product of exponential of quadratic terms. No? So if you take the negative logarithm of what we've seen before, we just extract the squared part, which is this one, and we also have a constant, or like a part which do not depends on E, and we can just, it's let's say constant with respect to the optimization. Okay? And we've seen this when we related maximum likelihood estimation with the Gaussian case to a least squares solution. Do you remember that? Okay. Now, it is a bit problematic if you try to do the same thing when we have a mixture of Gaussian, because we cannot put the we cannot push the logarithm inside the sum. Okay? So this is not possible because there is no rule that allows us to put the logarithm inside. This means that we cannot express this problem in terms of a least squares problem. Okay? One way of solving it, or let's say one way of going around that, is that if you consider that these two hypotheses or these two cases are often a bit far apart to each other, we can substitute the sum with a max. No? And if we substitute the sum with the max, we can push the logarithm inside the max. Okay? So here we are saying, originally we want to have a sum of different Gaussian with their own weight. And now we are removing the sum and we are just taking the max. Okay? The reason that we are doing this is that the Gaussian goes very quickly to 0. So this exponential function, it goes very quickly to 0 after 2 sigma, 3 sigma, and so on. And it's almost 0 everywhere, which means that if we are around this area, and the two Gaussians or the two modes are far apart, the contribution of one to the other is negligible. Okay? So if you are around here, this all sum can be approximated by just something here. If you're around this area, it can just be approximated by only this component. And if you are here in the middle, that's where we actually need both of them. But we are just saying it's very hard to end up here in the middle. Okay, so that's the assumption that we do behind. If you look at several cases, what will happen is that along this peak, we don't have much difference. So this is the max version, and this is the sum version. Around the peaks, there's not much of a difference, as you can see. They just shifted up and down, but the relation with the peak and the surrounding is not much different. Therefore, this means that we are not really changing the minima of these functions by taking the max. The only thing we are changing is the maxima, actually. The only thing we are changing is what happens in between. And the only problem that we might have is if those two are very close or there's a big overlap, that actually means that these things will be pushed and will be the new maximum. Okay? Because in this case, we are making a gross approximation because we are changing the mode of the distribution. But in general, the cases where this is needed are cases where those two modes are far apart. Okay? So if we do this max approximation, then we can easily move the logarithm inside. The reason we can do it is that we are maximizing something, and so we are taking the max of something, and we are taking a monotonically increasing function of that. Okay? So since we want to take the maximum, if you take a function of a value that it increases monotonically, we are not changing the order of the values in some way. We are only changing how they are squeezed together. So the maximum will still be the same one as before. No? Does it make sense? Okay. It will be different if we take a monotonically decreasing, because in this case we're just flipping it over. It's like when you have a inequality and you multiply by -1. Now that will be the thing where you change the order. Okay, so therefore we can push everything in, and this basically means that we are changing this whole problem into, let's look which is the most likely hypothesis where I am right now in my optimization step, and I'm just committing to that one. Then I do my full iteration on Gauss-Newton, and then for each of these constraints, each measurement again, I will check which is the most likely hypothesis, and I will commit to that any longer. Okay? So it's more or less a lazy way of committing on an hypothesis. In the initial or the standard Gauss-Newton case, you are committing before you start your optimization, and with the max mixture, you are committing during the optimization process. So if there is enough evidence that one hypothesis is wrong, you basically, if you have the second one, you can completely discard the wrong one and stick with the good one. Okay? Does it make sense? Okay. Is there any question so far? Okay. Yeah.
On the border between two mixtures, I mean, since Gauss-Newton is basically a gradient descent method, are we having like a problem with the continuity of the function?
Yes, we have it, but the gradient will always be defined. So the point is that by committing on one of the two, you still have the gradient defined for one of them. It's a bit tricky because the way you compute the gradient is like we first commit to one and then we compute the gradient based on that. If you do the gradient fully, there might be like a cuspid.
Yeah.
That's what you're saying. So there is no gradient. But since we are not really getting so mathematically, or actually more than mathematically, computationally, we are not computing the gradient going from left and right. We are just committing and then making the gradient. If they are exactly the same value, you will just, by the random number generator, pick one of the two. Most probably you will pick the first one. It depends on how you implement the thing. Because you will go through the modes and then either saying less equal or equal, and you commit and so on. So that's how you kind of go around there. The point is that if you are at the border, you're anyway in a place where you don't want to, so anything can happen in some way, no? You always want to try to push on one of the two sides. You have the problem in one iteration, the next one, maybe something changed, and you get somewhere else. Yeah, good question. Yeah. So how do we actually implement it? That was I just had a bit of detail. You basically just have a stack of measurement on one edge. You go over all of them. You pick up the one with the best one, the one with the max, and then you just work as this was the only measurement on that edge. And then you do the same thing as you did before for Gauss-Newton. So you linearize, you build the linear system, you solve the linear system, you compute the increment, you update the increment. Okay? Yeah, that's exactly what it's written here. Here you can see how it works in practice. So again, on top we see a different level of outliers. Each red line here is one outlier, one measurement. And the way this thing has been implemented is that each of these red things has two hypotheses. One is that is true, and the other one is this is not a real measurement. And by saying it's not a real measurement, it's like a uniform distribution. Since we're using Gaussians, it means a very flat Gaussian that can be everywhere. No? So you will have something that looks like this. Let's put it in 0 in this case. You will say, I have a nice Gaussian distribution that says I can be more or less everywhere, and you then have your second thing, which is that's a real measurement I get. No, that's somehow the idea behind that. So when you when you're outside of this, you basically your gradient will be almost 0, so you really are not influenced, almost not influenced at all by this measurement. But if at some point your whole optimization will bring you somewhere around here, then you will pick up some gradient and you will go on the peak. So this measurement will be active in some way. Okay? And here you can see that it's able to robustly tolerate a lot of these outliers. The reason that it works well is also because all of these measurements are actually kind of very isolated, and they do not build up in a consistent way. No? So you will have that all these green guys somehow form a consistent chain of measurements, and there is a lot of them that really puts a lot of consensus on this configuration of the nodes. And then there is a very spurious number of measurements that are just scattered around. And since they cannot build a unique consensus, but they're really scattered left and right somewhere, it's hard for them to take over the consensus set. No? In general, when you have robustness, you say, if I have more than 50% of mistakes, it's hard to recover the right solution. But in this case, it's slightly different because you have, let's say, a certain amount of points that all commit to one solution, and then you have a lot of scatter things. And the only way for the scatter to win is that a number of scatter points, more than the one that goes to the unique solution, are all pointing to another solution, which is the wrong one, which is normally not the case in real world, because if you make a mistake, it's hard that you make it 2, 3, 4, 5, 10, 100 mistakes that are all consistent to the single thing. Okay? So that's the main assumption behind. You have a question?
Yes, but I'm still wondering what you have drawn a flat curve.
To the graph here, this will be on one edge. So you will be one guy here. This will be each edge, either being green or being red, is now, this one will be the original edge measurement. And on that, we add this flat guy as well. So on this guy, this will be P of Z given X. Now, that we put in here, this is, I don't know, Z1, first measurement. Okay? And the way this distribution looks like, it's like this. Now it's an simplification because that's in 3D, or I mean, it depends on which problems we have. But let's assume that it's a nice 1D case. That's how the distribution look like. Okay? Another thing that we have here is the runtime analysis. So since the only thing that it adds is this for loop over all the measurements from each edge to check which is the most likely measurement, there is not much overhead because it's very, compared to computing the gradient and solving the linear system, that's really like a small step to do. And as you can see, I mean, besides the beginning where there is not so much to see, but you can imagine it's just a slight, almost a constant shift in computation. It is still, you can say, one part of the computation has been doubled or 3 times or 4 according to how many components you put on that. But comparing to the full cost of solving the problem, unless you reach really, really large amount, actually not even that case because the complexity of solving the problem grows roughly in the same way as the number of edges, if it's a sparse system, even if it's not a sparse system, because you can get square number of edges. So basically you will always have the same block, and the ratio between the first one and the rest will be always small. So you really have a very, very small increase in computational in computation, which is just a constant factor, which is a very small constant factor. Okay? So regarding outliers, a different way of using this max mixer. So right now we just saw the main framework, and I give you a few examples. But in principle, there are 3 ways of handling this. One is really for multimodal measurements, as I said, for instance, the slippage case. One is for outliers, so when we have failures in an association, and you can also mix them together. So here you can see a few different shapes, for instance. This is when you have correct or false measurement, and we're now putting everything at 0 as the ideal case. No? In this case, the measurement will be, these 2 places are the same. That's why there's a 0 in the translation. And of course, the outlier case will always be very flat Gaussian at 0. Okay? Because we don't want to put any bias. If there is an outlier, we just put at 0 as a mean of the measurement and very flat uncertainty. Or you can have different hypotheses that can be like left and right. And still you can add an uncertain like a mistake in the association, or this measurement is an outlier, gross outlier with different hypotheses. Or you can also have just 2 different measurements, or 2 different hypotheses, or many different hypotheses on one measurement. This will be the case with slippage and without slippage of the robot. Okay? You can also have another gross performance on a 3D case. Here you have standard Gauss-Newton, where only in outlier case, so we are having 1 outlier in here, and on the right we see the max mixer case, where each measurement has this double check, if it's a real measurement or an outlier. And the more outlier we add, you see that this whole sphere gets deformed up to a certain part where it just collapses again on itself. And with the max mixer, you're able to handle that. So it's one way of handling these outliers. And I'll now show you another way of handling this. If you look just at the cost function, you actually change the cost function a bit. So if you now look at the standard least squares, which is again minimized x, which is a sum of square terms, and we can call it this chi-square. We call it normally chi-square because this value here is usually distributed according to a chi-square distribution. Chi-square distribution is just if you have a lot of variables which are normally distributed, you take the square of them and you sum them up. They are then distributed as a chi-square distribution. It's just a definition. And therefore, you will see often the part inside a least squares problem to be called chi-square or chi if it's the square root of that and so on. Okay? Now, if you look at this, you can also look at the whole problem in a slightly different way. So instead of saying I have two hypotheses, like the flat one and the picked one, you can say that I have a lot of different hypotheses on my covariance, and that can be scaled by another factor. Okay? So let's say before I had two hypotheses, flat and picked, and now assume I have an infinite amount of hypotheses that go for completely flat to super peak. Okay? And this actually has this effect of scaling up to all possible hypotheses. So instead of just selecting one or two, I'm trying to find the optimal value for S so that I can select which is the right scaling for my case. Okay? If I want to do it, we can do analyze this problem as usual. So we now have just n additional variables. Before we just add the variables on the state space, and now we have the variables on the state space and S, where S is our new variable. If you take the gradients of this and then you do some magic and analyze, which is the minimum of this cost function for S given everything else fixed, you end up to have an update which is like this. This would be the solution. And then to avoid S to grow infinitely, so to give more information on what's really in the measurement per se, we cap it to 1. Okay? So the idea here is that you don't want to be better than what you can really be, but you still want to be able to remove things on the side. Okay? Does it make sense? So you want to be able to scale it, but not to make it bigger than what it is. If you look at this from this picture point of view, let me delete a few things for you. If you look, so before we had a very flat one, and then this was our original one, okay? If you now put, let's say this is our 0, and that's everything in here. If you now say we can scale, if now we say we only have our original one, okay, but we can scale it, we can say we can put S very small so that it's the information matrix, therefore the inverse of the covariance gets scaled a lot. We get something like this, no? The more we put the S to 0. The more we put the S to 1, we have something like this, as we have. If you now put S bigger than 1, we end up with a covariance which is much more peaked, which in terms of information content, we are saying the measurement that we have is better than what we really got. And that's something that we want to avoid because we don't want to make decisions based on information that we do not have. So we are basically saying, by taking the minimum of the two, we're saying we can discard something or we can keep it. And by discarding, we say it's a soft discard, so it can be weighted accordingly. Okay? Here, I think this should be, yeah. So basically it means that in this part here, they have the same error, the original Gaussian in black and the scaled version. And outside, you actually get the scaled version, okay? And if you look at the gradient, I think there should be a video soon, you can see that it's always getting flat. And the more you go there, the less you are including the measurement into your optimization. So this is just a way of showing how it happens. So whenever we have an initialization that is in here, it gets the same, and otherwise it gets scaled. This you can see it as an infinite amount of different. This is the next one. You can see it as a lot of different hypotheses, and you select the maximum one, but you do it implicitly, not explicitly. And the way this S is computed is we are at some point in our optimization here. That will be that's where our chi-square brings us, okay? And according to where we are, can get S equal to what this should be equal to, and this gives us the correct covariance in that case. Okay? It's the same as we did before with true cases. It's just that now we have an infinite of cases and we are in the continuum level deciding which one is the right one. Okay? So that's what this dynamic covariance scaling does. Any question on that? Is it clear? Yes? Good. This brings us to the final part of the robust lecture, where we can put all of this into one big family. And the thing that we did so far is that we always assume that there is a Gaussian distribution that our errors, our measurements, noise, are always distributed according to a Gaussian distribution. Okay? And the problem here is that this error model is not always realistic, so it's not always the case. And when we have large errors, these are problematic, okay? Because under this Gaussian model, the further away we go from the mean, and by further I mean in terms of amount of standard deviation, the less likely something is, okay? Which means if you get something very far away, let's say somewhere around here, the optimization will try to think this is very unrealistic, it's almost impossible for this kind of error that this happens, therefore it means I have to make a trade-off and I have to come as closer as possible, okay? And you will see that this is something called light tail, or there's not enough kurtosis in this distribution. That's like a way of analyzing distributions. But there are some other distributions family that are called heavy-tailed that are actually giving more probability or more likelihood to events which are rare. And rare means that are far away from the mean of the distribution. Okay? If you now use these distributions as your likelihood model instead of a Gaussian, you end up in something which is called M estimations, because it's a maximum likelihood like estimation, that therefore the M stands there, because you can see them as a maximum likelihood estimation with a different likelihood model than the Gaussian model, okay? And you can say that these are like with heavy tails, and you can also, the framework is built in a way that there is a row function that can define the density function. This is one way of seeing it, where you say the distribution belongs to the exponential family, okay? And you can write it as exponential of minus rho of E, okay? But some of them have a different form, so there is no exponential involved. But the whole point here is that if you take rho is connected to a potential likelihood, because rho is actually the log likelihood of, it's connected to the log likelihood when you have a likelihood model for that. For what concerns you, imagine this rho is basically something where you put the error around, okay? So in case of the Gaussian likelihood, this rho is just the square, okay, or the norm, the square norm. If you have different, we'll see later on, different families of rho, these are actually just a way of defining different error shapes, Okay. Now, some of them have a way of getting from here to the distribution, to the likelihood. Some of them, they do not admit the likelihood because the resulting P here, written in this way, does not meet any integral. Okay, so you try to make the integral to normalize the distribution, that doesn't exist. Okay, so you cannot normalize them, therefore they're not the proper distribution. But you can still use them into an optimization point of view because there you don't care about the fact that it's not normalizable to 1. Okay? Now, few cases, we have the Gaussian. As I said, it's just the square of the error. You can have the absolute values, so, or as it's called L1 norm of the error. And this is actually equivalent to have a Laplace distribution as your error term. You can have what's called the Huber M estimator, which is a combination between the two. It's in the middle behaving like a Gaussian distribution or a squared error. And it's then behaving like a Laplacian distribution or a L1 norm after that. So it's something like, I think I have a picture later on, so I will show you later on. And there is also a lot of different distributions. So it turns out what I've shown you before, both the max mixture in a specific case and the DCS, the dynamic covariance scaling, are actually a form of M estimators, and we'll see how they look like. So here is Uber, and I don't know if you can actually really see it, but it is square up to here, and then it just goes straight. Okay. While if you wanted to do a square, this will really go up here very quickly. And this is quite good if your outliers are not too big. So if you have somehow something which is close by, and you can have an outlier, but the mistake is not too big. Okay. So let's say I'm here, but instead of saying I'm here, it says I'm here. Okay. Then that's because the effect of the outliers is still put into the minimization. There is still a gradient, but the gradient is way lower than the gradient that you will have if you consider instead of a squared function. Okay. There's also a particular thing about this guy, is that it's a convex error function. Okay, and it's one of the, let's say, more robust convex error function. L1 will be a counterpart where you also have the square, the linear things in there. And it's very useful if you have a convex minimization problem, if you have a linear least squares or at least a convex least squares. Okay, so let's say a linear least squares. Well, the problem here, let's go in the beginning, the first slide, where the sum is linear. And I'm telling you why in a second. So, yeah. So if this E here is linear, so it's not a nonlinear function of the state, but it's just a linear function of the state. So the usual thing, AX minus B. The interesting thing of using a Huber is that you still have a unique solution. Because this is a convex function, you put it into a linear function, the result is still a convex function, okay? So it has, let's say, the same characteristic of a Gaussian, because there is only one minimum in the cost function, but it's still more robust than a Gaussian. So if you have a convex problem, this is a good choice, at least as a beginning. The bad thing is that it doesn't really work well if you have big outliers, and that's because it doesn't matter, once an outlier is bigger than the parameters you put here, so the C half, the bandwidth, it's treated the same. It can be here, can be here, it can be there, it will have the same effect. Okay? Less than it will be for a quadratic, because for a Gaussian case, and then therefore a quadratic cost function, you will have that if you have an outlier here, we'll have effect of 1, here we'll have effect of 2, 4, 8, 16. So the further away, the stronger the effect. For Huber, the further away, the same will be the effect. Means the magnitude of the gradient will be the same in all cases. We have then, that's the L1 norm, the Huber. Then we have this other family of guys here. They are called redescending M estimator. This one is a slightly different case, so we'll treat it later on. But this one, Turkey, they're called redescending because they go up and then they stabilize themselves. Okay, so they basically do not go to infinity on the side, but they will go to one number. Okay, Cauchy is slightly different. Cauchy goes to infinity, but it goes to infinity very slower. The effect of this is that the further away you go from the zero, the lower is the gradient. So we go from a Gaussian or quadratic where we are here, and the more we go away, the more the gradient is picked. We go then to L1 norm or Huber, that the further we go, the gradient is the same. Two redescending cases, these three, where the gradient goes like this. The further we go, the flatter is the gradient. So the less is the influence in there. So these are very good for corrupted, or let's say, for gross outliers. Okay? Because you're really eliminating the effect of the outlier in the minimization problem. The corrupted Gaussian is like a Gaussian. It has the effect that when you go far away from the center, the gradient gets bigger and bigger. But then there is a flex here that actually changes the behavior. So it goes from a behavior like this, then goes like this, and then again like this. Okay? But the gradient here is anyway very flat, that will not influence too much the rest. This is what actually happens if you use, instead of a max mixture, a real mixture with the sum by using these two cases, no? The bigger one and the smaller one. No, that's what happens. Dynamic covariance scaling is slightly different. It looks more like, I don't have it here, but let's say it looks more like something like this. Okay? And another difference is Cauchy. Cauchy, as I said, it doesn't flat, it doesn't have an asymptote on a number, it goes to infinity. And that's also the reason why you can define a distribution for Cauchy, which is, as you can imagine, the Cauchy distribution. But it's less resilient than Blake-Zisserman and Toki in terms of gross outliers. And for those two guys, that they have an asymptote, so they go flat at some point, there is no way you can compute an integral of the corresponding, it's called phi function, so the corresponding distribution, because it just doesn't go to zero. If you look at it from a negative exponential point of view, you will see at some point they just go flat. So if you go to infinity left and right, there is no way of removing stuff. You will just add a constant at infinity at some point. Now, while this one will go to zero eventually, and will actually converge. Okay? Does it make sense? Any question on that? And there is plenty of different guys in here. There is also like a student, which is an extension of Cauchy where you have a parameter that you can play around. So there's the whole field of M estimators with different row function is pretty broad. Okay, this is a difference between the corrected Gaussian and the max mixture, as you can see. Max mixture just has this transition phase, and the corrupted Gaussian has somehow like a smoother version there. Again, there is a problem of gradients here if you just do it mathematically, but if you just select one of the two, you wouldn't care, because this will just give you a bit of push in here, and then you're soon inside the other guy in the next step. Summarizing a bit robust estimation, it's very hard to understand which robust function you want to use for which problem, but it's good to get an idea on how they behave, no? And the idea is that, as I said, there is this Huber, which somehow can cut some outliers and has a certain effect. And for me, the good thing of understanding it is to how the gradient behaves when we are far away from the mean, no? From the mode. If it goes stronger, if it stays the same, if it goes weaker, and so on. Okay? So that's, I think, something that, at least for me, makes me understanding what's happening inside. Again, like max mixture is similar to a corrupted Gaussian. the Uber is used if you have, if you don't know anything, it's good to do as initial guess. It will not introduce any additional minimum in your problem, while redescending functions might introduce additional minimum. So it might be that you end up in a minimum, which is not the minimum of your original problem. And that therefore people do not tend to not use them, especially in computer vision. And finally, also dynamic covariance scaling and max mixture are kind of, so a particular case of max mixture are kind of robust function. So this somehow, so the conclusion of the lecture today is it's good to have something which is able to deal with some error from the data association point of view. The reason is it's very, let's say, preposterous to assume that there is perfect data association, that someone can solve data association for you. And it's very hard from a data association decision algorithm to make no mistake whatsoever. Okay? So the only way it can make no mistake is if it doesn't give you any answer at all. Okay? But that's not something that you want to have. So at some point you want to be able to get as much answer as possible because they influence your accuracy. And you want to get at the same point, same time, a very low number of wrong wrong association from your front end, so that you are still able to handle them in the optimization part. And we'll talk about front ends next week, so you can see what happens in reality when we are trying to make this decision. Is this the same place or not? And the interesting thing of what I present so far is that it really fits well within any minimization framework, because what you're working on is just changing a bit the way the cost function works, but not the whole structure of the problem. And I haven't shown it here, but when we use, for instance, any gradient descent or Leibenberg-Marquardt-like algorithm, there is actually a way of just computing the weight out of the gradient update. So what you've seen here in this case, when we are trying to do this, we can just use a standard minimization algorithm that does a least squares when this row is the square. And there is a way for a lot of row-based M estimator to compute what's called the weight function, okay? And then we just can give to most of the implementation like a weight. And this weight can be put inside the covariance measurement, the information matrix, whatever can scale your error down, okay? So you don't need to rewrite the code of the minimization. Sometimes you can just change the behavior, the cost function, by changing the input that you give to the problem itself. Okay, so that's an interesting thing on this M estimator thing. Right, that's also what it means here for minimal code changes when you have to integrate them. Regarding the literature, there are 2 papers on the web page you can look. The first one is on the max mixture. The second one is on dynamic covariance scaling. If you want to have more info on M estimator per se, you can just go on Wikipedia. There is a lot of information on that, robust estimation, and have a look at that. Okay, so that's it for the first part. Okay, so the second lecture of today is about Toro. Toro is just an acronym developed in the lab here, but it's a way of doing gradient descent for SLAM and specifically stochastic gradient descent. Does any of you know what stochastic gradient descent is in general? No? Okay, so do you know what gradient descent is? Now you take the gradient of the cost function, you just follow it down, and there are some rules to decide when to stop or how far down you want to go. The stochastic version is saying instead of taking all your data, you just take part of your data and extreme just one data point, and you compute the gradient of the whole state space just considering one data point or a subset of your data. And the stochasticity comes from the fact that the way you get which data to use, it's random, it's stochastic, so you get some random pooling or some random subset. So you can do the same for SLAM. And the idea here is that the minimum measurement that you take is just one single edge. So you take one edge at a time, randomly, and you can compute the gradient of the full state space, or actually part of the state space, just considering one single gradient and using what's called an incremental parameterization. Okay, so the idea here is that if you parameterize each node instead of with their absolute position, but with the increments over the temporal time where they've been acquired. So each of these will just be like the post before plus minus something, the post before plus minus something. What you will have is that this measurement between these two will depend to all the paths here, all the paths here, until they get to the common ancestor. Okay? Therefore, you can update a lot of different nodes with just one measurement, and you don't and you change the whole path here, and not just the position of the two. Okay? Because in the worst case, if you just take one measurement, it would be clearer after that, but I just want to give you an idea. If you have something like this is your post graph, let's assume. This is the measurement you're taking right now. If you have an absolute parameterization of this, when you take the gradient, this will just say, this node should go maybe in this direction, this node should maybe go in this direction. And the only thing effect you will have is that the next step you will have update here, but you will still have no change at all from the previous part of the graph. Okay, so you will only update these two variables. It doesn't bring you anything. Okay, because then you will have to adjust all of them. There will be a lot of oscillations around. The only way to make it somehow meaningful for SLAM is to, from each measurement, to actually get the whole path, so to get an update for all the nodes. And we'll see how we can do it. But there are still some other problems that sometimes solutions might be contradictory, because you might say that you take this measurement, everything goes left 1, the gradient, then you take another measurement and everything goes right 1. And if you keep on obtaining one left and right, you will just oscillate forever without finding any solution. And for addressing this, there's something called learning rate, where you just scale a bit over time, so that at some point you know that you will stop, the algorithm will stop. You're not sure you are in a minimum, but you're sure that the algorithm stopped. Yeah, so, and the idea here in picture, as I've seen here, I've shown before, is like you take this measurement, you compute the error, you distribute it, you iterate everything, and at the end, hopefully, you get with the correct solution for your graph. Now, there is what has been used in literature is what's called preconditioned SGD. So preconditional stochastic gradient descent, and preconditioning is just something that says it's a matrix that I use to scale my gradient. Okay, and the reason one uses it is that you can put some structure of your problem in your precondition. In this case, is the inverse of the Hessian, so that you know that some direction should be treated more or less. And you also maybe know, for instance, you can say, I know for sure that some of my variables are this value, and you can put it into the preconditioner. So because then, whenever there is a gradient that moves these variables, you will just put it to 0, no? And you keep them fixed. So basically, the preconditioning is a way of, you can see either do a change of variables, influencing the behavior, changing the metric on your gradient descent. And you do it to speed up things, because you can put prior knowledge or other things which are one level above the gradient, like the Hessian or other information in your state space. And the whole idea is simple. You take the residual, okay, the residual of an individual measurement, R, or of a set of measurements, and the residual is the negative of the error. So you just take the, basically saying, the error tells me that I am here and I should be there, and the residual is what pushes me there. So it's just the way you define the sign between the two. No? You take this, you multiply by the information matrix of the measurement itself. So it says, I'm most sure in this direction than in the other one. So you get much more push in the directions where you're sure. You take your Jacobian, which is the one that maps your measurement to your state space. The preconditioner, in this case, we use the Hessian of the whole state space, so the one that you incrementally update over time. And then this lambda here is this learning rate, which just, there is some rules to put in smaller and smaller over time. And this defines your update rule, okay? So before we defined update rule, the delta x as a solution of the linear problem, where we say h delta x equals minus b. And now we define our delta h in this way. You then update your estimate, x times t, with this increment, and then you get the new solution. So the only thing that left to say is what is the Jacobian and how we can compute also the Hessian and the rest. And the Jacobian depends on how we parameterize, of course, the state space. And that's the difference that I said if you use something like incremental parameterization where everything is influenced, or just an absolute parameterization where only the two nodes are influenced by the gradient. Now, this is a bit abstract, but I hope it will help you somehow. So in the state space, there are the parameters of what you're trying to achieve, okay? In the classic standard way, you can imagine you parameterize everything as absolute coordinates. But you can also define any kind of parameterization that you like. No? It's just to say, this is the real entity. I can parameterize this real entity with something, and I work on the parameter space. One maybe intuitive way is if you do rotation in 3D. Okay? So you can parameterize a rotation by Euler angle, by quaternions, by rotation matrix, and so on. Okay? So this is a set of different parameterization. They all express the fact that this thing is oriented like this in 3D space, but numerically they're different. And when you then compute the gradients depends on the way you parameterize things. Okay? So that's the example here. And you basically have this G, which is a mapping function that goes from the parameters to the poses, and you also have an inversion between the two. Now, so you have a bijective mapping between the poses, which is the 3D or 2D real places in the world, and their parameters. Okay, so that's just to give an idea what's explaining here. And when what you're actually doing is you optimize, or you find the solution to the least squares in the parameter space. So you can, if you have an error which is defined in pose space, you can also just report everything back into parameter space and vice versa. Okay? That sounds complicated, but it's just a way of saying we're not doing anything strange, stupid, or wrong. It's just we are changing the way we look at the problem, but not the problem itself. So there is a first approach of stochastic gradient descent by Edwin Olson, and he used what's called incremental parameterization. So he's basically saying, I just consider, let's say, the odometry chain, so the poses at different point in time while the robot goes around in the world, and at each point I parameterize, so X my parameterization, using the absolute difference between the two poses. So the poses at time I and the poses at time I minus 1. So it's really like minus. There are 3 values or 6 values, 3 values or 6 values, you just take a difference of them. Okay? Very brutal, but works quite well. And the reason is also that if these are very close in space and time, the real transformation, it's very small and it's very close to a subtraction. Okay. Now, it's related to the trajectory, and the only problem, let's say, is that you ignore somehow the topology. Okay. You will see later on what it means, but it means that if you're now going over and over and over and then coming back here, the relative parameterization of the nodes very close to me will be with the one before and not with the one right now. So the connectivity in some way it's not taken into consideration. So whenever I need to update something here, I have to update all the variables of the whole loop up to here, while I could maybe just take this one, rechange the parameterization, do something like a spanning tree in some way, and then propagate the things around in a better way. But there is, again, another parameterization that does exactly that. So it takes the tree and parameterizes over the tree. Now, that's the exactly this. That's the second parameterization. So we can take it from the topology. And what we do is imagine this. This will be how the initial increment of parameterization will parameterize all the nodes. So basically, 9 will be in 9 will be pos 9 minus pos 8, in 8 will be pos 8 minus pos 7, and so on. You can then compute a spanning tree out of this, and you will end up in something like that. So you can also have a parameterization that it goes 9 is attached to 1, and then you have these things out. And the interesting thing here is that you have a very nice way of computing these values by just propagating forward your information from the tree. And then you can use these off-tree links as your stochastic gradient descent measurements that adjust the whole link back. So you basically not only define a different parameterization, but you can also define a more deterministic way of sampling the measurement that actually has a better property in terms of convergence and accuracy of the solution. The idea here is that once you have this tree, you can parameterize it in this way, and the second parameterization, in this case, that's been introduced by Grisetti et al. And the idea here is that instead of doing the algebraic mean minus, it does the full transformation minus. Now, so like you have these two transformation in homogeneous coordinate, so you really take the equivalent of minus in that group, which is the inversion of 1 and the multiplication, okay? And you can see that there is this tree, there is an up chain from here, there is a low chain, and there is a measurement in here. And the error is exactly this, is you take the down chain, then the other loop is the inverse of the up chain with the delta, so which will be this with the delta, inverted, and this whole thing should go to 0, okay? So whenever you close a loop, this whole thing should be 0 because it's going around the same area, okay? We can now divide the measurement into different classes. You know, we have the loop measurements and the open loop measurement, which are the one that are connecting the branching in the trees. And the loop one is the one that connects two different branches. No, there will be the red one will be the open loop ones. The blue one will be the loop measurement that we have there. And what we do is that each stochastic gradient descent equation solves one problem at a time, because we take every time one open loop measurement for stochastic gradient descent, okay? And we are taking one, solving it, taking the second, solving it, taking the third, solving it. Once we took all of them, we adjust the learning rate so that we go, the update is actually less than the one at the step before. And there is, all in all, the approach there. Now, how do we do the update? You can see here, this will be the classic or the standard rule for the stochastic gradient descent. So what still needs to display or understand is how this Jacobian is computed considering the parameterization that we are using. Okay, and the interesting or the complicated thing is that 3D rotations are nonlinear, and if you just update according to this one, you have poor convergence. Okay, the reason is that either you end up in something like this, where you have very small connection if you don't use the incremental parameterization. Or if you use the incremental parameterization, which is just the sum, you would just have an interpolation which is a linear interpolation over there, because that will be given by the Jacobian. But what you want to do is that you want to have an interpolation on the rotation space. Okay, so the example in 1D, maybe it's easier. So imagine now, you all know rotations in terms of, you can express 1D rotation with an angle, of course, but you can also express them with cosine and sine, okay? So you can see that the rotation as a rotation vector, it's something that is lying on a circle, okay? Now, if you use the linear, the incremental parameterization, but the linear one, you will end up that if you have one rotation here, so one vector pointing there, and one vector pointing here for another rotation, let's say, when you try to interpolate them linearly, you will just get something on this line, okay? So it's not really, it's not a rotation any longer, and to keep it to be a rotation, you then need to adjust it. And it's also not the real interpolation, because here you get not so, you get very slow change in angle, as you can imagine. But here, with the same change, you get very large change in angle. No? So the difference of the different angles that you interpolation is not related. If you do it on the what's called the manifold of the rotations, what you will end up is that you will have something which is linear on the circle, which is what you really want to do when you want to spread the error. Okay, so and that's the idea here. This will be the update, the classic update. With the incremental linear parameterization, you will do a linear interpolation on the J, and now we can do something which is in spirit similar to stochastic linear descent, but we will instead use a spherical a circular or a spherical interpolation for that. Okay, and that's what I'm going to explain next. Imagine you have this as one chain. Okay, this is the the other pose which is connected by the off link of tree link, and you want to put this thing together. Okay, so these are the same pose, and this will be the measurement of the tree, and this will be the chain on the tree. Okay, so the idea here is that this guy and this guy should be the same. Now, when you put them all together, you would like to reach something where all the nodes are updated, and you want to first, you can do it together, rotation and translation, but what actually works better is to first distribute the rotational error. So you just try to align everything so that the orientation of these two is the same. And you do it using this. The idea is the same as here. It's a spherical interpolation. And once you have that, you can just then linearly distribute the translational error, as will be just a sum in the incremental parameterization. How do we do the rotational error? You can, so mathematically it's a bit complicated, but the idea here is that you want to find a set of rotational metrics, so R1, R2, Rn prime, such that when you take the old one, and then you take the update that you need to do, they will end up to be the same at the end. Okay, so applying this set of rotational metrics or applying the original one plus the residual should end up in the same final rotation. Okay, so that's what this thing says. And you want to have them incremental, therefore you have this application on that. And you also want to have them in a way that respect this kind of interpolation scheme. Now, we assume that the first one is the reference frame. Okay, so we are saying, imagine now we just have R1, B, and R prime 1. Okay, that's easy. We just say A prime is equal to A and B. Okay, so we are basically just saying this last part is equal to this. And now we have to say how much we have to transport back of the error. Now, if you write now as rotation in the global frame, you can also say that there is a certain Q, which is our first frame, and AN. When we then decompose the residual into a chain of incremental rotations, we will see that this is the final rotation that we want to achieve. So that goes from the original frame to the final one. This has to be divided in a set of incremental rotations, okay? And to compute each of them, we do what's called a SLERP. SLERP stands for spherical linear interpolation. That's what does this thing here. And this U, K minus 1 and UK are basically the small increments in here. And the way we compute them is to considering also the uncertainty in the rotation. So the more certain rotations will have a stronger effect than the others, okay? So, but the idea here is that you want to uniformly sample, not sample, but divide the space between these two rotations such that you reach from a small step, from a set of small steps, the whole difference that you want to get. So the Q there. Here is an explanation of how SLERP works in 3D. It's been used for 3D animations. The problem there was that they wanted to like interpolate, for instance, arms going around. So they want to define keyframes in 3D animation and make sure that the full animation is actually meaningful, looks realistic, and so on. And the idea is that they want to have something which is called constant speed. So constant rotational velocity, which also means constant displacement on the arc or on the sphere if you are in 3D. And you want to have properties like this, that when R prime is equal by definition SLERP RU, so it's always having one rotation and one level. And this R is always considered like the initial one is at 0 and then there is the R there. So you always interpolate between 0 and R. That's the definition of SLERP. And you can imagine now as axis angle, you find the axis of this rotation, and you just do a linear interpolation on the angle, okay? So that's how you can imagine this thing. But of course, this will change. So the axis is this. The angle will be u of the angle of that. No? So like you define which is the angle, and you just rotate linearly around that. Now you can. It's not that trivial. So you actually do it. I'm not sure if, okay, so it's not explained here, but what you can do, the way you do it is basically using quaternions, and you can use the whole interpolation using the exponent of the quaternion. So, but I'm not going to ask at the exam, so it's probably too much of a detail. If you really are interested, you can look for it and see how it works in principle. But just know that it works, and it does an interpolation on the sphere or on the circle if you are in 2D. So once we have the individual small transitions, the small rotation individually, we can compute each A prime k by just applying all the rotations up to k and taking the A of the k that we computed before. Okay? So we can also see the same thing as R prime k equal to A prime transpose k minus 1 and A prime k. Here, this basically means the inverse of the A prime at k minus 1. And this gives us the relative rotation. So the whole point here is that for each time for each time step in the chain, we are comparing the incremental parameterization, which is the one given us by Rk, to the absolute parameterization, which is the one gives us by the SLERP. Okay? Because we always want to get back to the incremental parameterization. And everything should be the same. So these all two views has to always be the same. Otherwise, we are doing something strange in the parameterization space. Because we want to make sure that whenever we do some change in the variables, that the change in the pose and in the parameterization are consistent. And that it's what these constraints are doing. Once you have put all the constraints there, this is just a constraint problem. So it's a set of equality. And you just need to find a solution for this set of equalities. And we can do it recursively. But just say the first one is equal to the first Q plus the original first rotation. And the second one, we can do the same. We just say this is the definition on how we get the second rotation. This is the definition of the first rotation inverse. So A prime K, A transpose K minus 1. And you end up in having this form. And actually, Q1 transpose Q1 simplifies because it's the same as the others. And what you are really carrying then is this R1 transpose Q2, R1, R2. No? And if you then go over and over and over, you have the recursive formulation made in this way, where you have the structure. There is the R's from 1 up to the K minus 1 transpose, the actual step that we are incrementing the rotation, so according to this, and then the chain again of them, and at the end you take the last one that was before. Okay, so that's a structure that it's everywhere, and you will just repeat it over and over and over. Okay. So you can show that the residual is actually bounded by this. So the change in rotation is always less than the angle of the incremental rotation that you do. And that's important because you're always saying we are doing an increment, we are changing something which is no more than the propagated error over the path. So we are always somehow staying in the deformation that we have from the measurement. And that it's also telling you that that whenever we have a potential error, the error is always bounded by that. Okay, so we are not making too much of a big mistake, or too big of a mistake in this case. And this is important for the reason that we are considering only one measurement at the time, and you don't want that this measurement makes too big of a change that cannot be corrected by the rest of the measurement around. No? This gives us a bit of guarantees, theoretical guarantees on that. So the only remaining thing is how to determine UK. And this is the parameters that determine how much of a rotation we want to take. So how we compute the incremental small rotation over the chain. And the way we consider it is considering two main components. The first one is the uncertainty of the measurement, and we only consider right now the minimum eigenvalue of the information matrix of the edge. The reason we are considering only one is that this U is a one-dimensional value. So we are basically saying we want to use the minimum of the eigenvalue of the information matrix is the direction with the most uncertainty. Okay, so if you have a very low information, it means you have a very high uncertainty, and the eigenvalues actually measures the directions of the, so the main directions of the uncertainty in 3D, 4D, 6D, or where you are. Basically, you are just saying, I want to commit the least amount of information. I don't want to be too much confident. And I just want to do an update which is good enough for the amount of information that I have. And the second thing you're considering is the length of the path. Okay? And that's because we want to have something that penalizes, does not much increment if the path is short. And that's what's in here, and we have a parameter that controls how much we want to do that. And otherwise, it's just computed by how many steps you have to go up and how many steps you have to go down. Okay, and that's the part here where this is the up part, I think, and this is the low part. Okay, the assumption here basically is that if you're considering spherical covariances, Okay, so instead of having ellipses, just spheres. This minimum eigenvalue there is the same in whichever direction we go. So there's only actually one value of information in that. The less spherical they are, the approximation will just make them spherical, but with the minimum eigenvalue size. Okay, this means if you have an uncertainty which is shaped like this, let's do information matrix so it's clear the mapping. So if you have an information matrix shape like this, so the covariance matrix is shaped like this, we take the eigenvalues, they look like this is the eigenvectors. The eigenvalues are this and this, not exactly, but the square root of them. And what you will do is, by taking the minimum, you will say, I assume this is actually something like this, no? So that my real information will be something like that. Okay, so that's what we are assuming in here. Once we have done with the rotational error, we can distribute the translational error. And the distribution of the translational error is, let's say, trivial because we just do a linear interpolation on that. So we have the final post, we have the initial post, we take the difference of that, and then according to the different information matrix on the different path, we just distribute this full thing with respect to them. Okay? So graphically, we have something like this, and we try to push all of them forward until they have roughly the same distance. Okay? So in summary, what the algorithm does is that we first decompose the problem according to tree parameterization. This basically means we do the interpolation thing and then we build this tree. We have seen one of the best solutions you get it if you do a spanning tree, but computing a spanning tree might be a bit computationally expensive, so you can still rely on the original tree, which is whenever you connect a node whenever you come back on a loop, so like the temporal index of a node in the next node connection will be lower, you just flip the direction and you have your tree. And once you have that, you have just a for loop that says select the measurement, and we can do it randomly or inversely proportional to the number of nodes that are included in the update. So basically the length of the up and down path. Then you compute the absolute values of these nodes. So you just propagate everything in absolute coordinate. You compute the delta, so the error in the measurement, the residual. Then you take the incremental rotation, you decompose it over the path, and then you propagate these deltas to the parameterization behind. After that, you do the translational part, so the same, you have these absolute values. You take the difference, you compose in the small pieces, and you apply the small pieces in each individual nodes. That's it. The complexity of the whole algorithm is in each iteration you touch all the measurements. So of course is linear in the number of measurements, and this will be this m. And also with respect to the average path length. That's because you take one measurement and then according to how long is the path, this will be one application of the residual over the path. And then you do it for all the measurements. So one iteration, when you consider all the measurement, is m times L. So it's linear in the number of measurement and in the average path length. Now, if you look at the graph, you can say you can already see, let's say graphically, that goes something like m log n. So because it has this nice shape in this way. The reason why it's m log n is that you can imagine that m is the number of measurement, and the average path length, if you do a nice tree, is actually a logarithm of the number of the nodes. Now, if the tree is balanced, the path length is roughly the logarithm of the number of nodes. Okay, it's not always the case, because there might be that the robot explore much more in one direction than another, so you need to change the initial frame. But if you really do it properly as a balanced tree, as you will do in algorithm and data structure, when you do search trees and so on, you can then have some more strong guarantees on the average path length. But in general, it gets quite close to m log n. Okay, so no theoretical bound, more like on empirical evidence, but that's roughly the complexity, or at least the average case complexity in some way. You can also do better, so you can also include some node reduction step that was done in the original work on Toro. And the reason there is that sometimes, so the whole complexity grows with the number of nodes and the number of measurements. And the more you are looping, the more you're going around a certain environment, you are sometimes not, you are adding a lot of nodes, you're adding a lot of measurements, but in terms of information content, this new node do not bring you much information content, because there will be snapshots of the environment very similar to other snapshots of the environment. So you want to somehow collapse them into single place and have a complexity that grows with the size of the environment and not the length of the trajectory. Okay? And the idea here is that if the robot is well localized, you can just say, okay, I'm not adding a new node, I'm just localizing in the node before, but I'm just putting the information that I have right now, so this, let's say, in the loop 2, and together in the information of the loop 1. And you can, similarly, you can update the measurement by just doing a weighted sum of the information. So does it look like something you've seen already, these two things? Do you remember any filter that does something similar? Yes? No? Maybe? No? Do you remember the information filter somewhere? Yeah. So basically what it does here is that you have two measurements and you want to fuse them together. And the easiest way to do it, since we are adding measurements, is through the information filter. We already have them in information form because we already have the nice information matrix. And the reason why we have now this omega minus 1 here, it's because we want to go back from the information vector, which is what you compute here, to the mean of the measurement. No? And so again, this whole estimation, optimization, information filter, common filter, they all kind of have the same background, the same reasoning in the back, and you can play around with the different pieces wherever you need and whenever you seem fit. No? That's one case where you can do a simple, small information filter to just get rid of some of the nodes where you build your graph. Okay? Almost done. So here we can see how it works in for different cases. Again, we use this nice FEAR data set, and you can see that according to the different initialization, of course, you end up in a different problem. Something is easier, something is harder, because they are far away from the solution. But after a certain amount of iteration, you can see that in most cases, so even in the hard cases down here, after only 50 iterations, it's pretty close to a nice shape. And when you get after 300 iterations, is very close to the final optimum configuration of the nodes. We did some experiments also on real robot. This is a car. Smart was retrofitted with a lot of laser scanner, and this here is at APFL, where the car just drove around and collected data. And here is the original data just using the odometer of the car, which was already good, but it had some error here in the orientation. So you can see when it came back, there was a bit of mistakes in orienting the car. And then after optimization, you can get something like that. There is a comparison also between the different parameterization. If you do the incremental parameterization based on the time index, and the linear difference, or if you do the tree-based parameterization using a spanning tree, and by considering the old topologies of the rotations there, you can see that you end up very close to the minimum much faster. Okay. The reason here is that if you have shorter paths on the tree, the error there gets neither propagated in the right way. Otherwise, you will have a lot of error propagated on one path, but not much on the other side. And if you put everything together, there might be a lot of other paths that actually want to change you left and right. So the closer you are, the shorter it is the path down the tree before you make an update, the better it is from the convergence point of view. And that's clear now here in these few images. If you further analyze these two different approaches, and you can also see that in here there is way less error, and that's also because of the incremental parameterization and further down. The convergence is much faster, as you can see from this here. And also the final error in configuration goes way lower with the tree approach rather than the incremental parameterization. That's the analysis done on these data sets. So these data sets here are basically randomly generated Manhattan world where the robot is just simulated to go either straight, left, or right. And it just does this maze of these Manhattan-style streets. Just a way to have ground truth of very large data sets without having to drive the robot around and then manually label each position on them. Respect to time, here is a comparison of different approaches. We have the first two is the also parameterization, so with the minus an incremental one. You have in yellow, it's called multi-level relaxation. It's something we didn't include in the lectures, but it's another way of solving the least squares problem in a hierarchical way. So you just go in a quartz structure and go down, similar to what we did in hierarchical postgraph. And then here you have these other two approaches, which is the tree parameterization with and without node removal. And you can see that if you do a node removal step, you get much faster, even if you add a lot of measurements in the graph. Another interesting thing is that you're also robust to initial guess, and it's also robust to outliers in a certain way. The reason to be robust on the initial guess and not outliers is that whenever you just consider one measurement at the time, you have a cost function which is much smoother than the one considering all the measurements. So you're basically giving the algorithm the capability of jumping from one local minimum to another by just allowing it to going freely in the parameter space. Okay? This doesn't mean that it's always better. It means that it can go in even worse local minimum, but in general, if you tune well the learning rate, you know your problem well, you have this possibility of going into a global minimum even if you start in a bad initial case. Okay, and here it's an experiment where it's been done with the same data set but built in different places to simulate a bit of 3D structure and repetitive environments that look like the same on each floor. And you start with a completely useless initial configuration, and you're still able to recover and get to a decent, good result. Okay? And that's just because the algorithm is able to jump between different local minima. There are a few drawbacks. One is that there is this separation between translation and rotation. The main drawback of that is what is called the staircase effect, or we call the staircase effect. It's that sometimes you end up in a situation where your solution is something like this, 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 this. Okay? And that's because you might start with something that has almost no correction with the, so imagine that the robot really did something like this, okay? Now, the correction of the orientation will not be changed. So we want to go in the same thing there. But when you then go on the translation, you will just shift them down. And if you then attach laser measurement to that and you want to project them down, you will end up, maybe that's a corridor, I'm just assuming, you might end up in something like this. No? And that's where the staircase effect comes from. And the reason there is that this correlation between rotation and translation has been neglected, and you just go in two phases, and you might have situations like this. They are not so common, they are kind of rare-ish, but they might happen, so just to take into account. The other thing is that assumes roughly spherical covariances, so it's hard to model measurements where you have this infinite corridor point of view, because they're not spherical at all. You're very well constrained in one direction and very well unconstrained in the other direction in terms of observability. And there's also some slow convergence. That's because of the learning rate. So to have it stop, you need to go down on the learning rate. And this has two effects that either you are stopping too early or you're oscillating too much, and try to find the right value is not so easy. And therefore, you go down very close to somehow a minimum, and then you will really slowly adjust until the learning rate goes to 0. And you don't have any measure of the errors at the end, because you don't get it directly from that, but you can still do it later on. So you can just then linearize everything at the solution given by SGD, and then do linear propagation of the measurement error to the state space. It's like just basically building the Hessian as a normal least square, but without doing any optimization there. Of course, you can also use a couple of steps of Gauss-Newton after SGD to improve the accuracy of the solution. Sometimes it's not possible, because sometimes one of the reasons you use SGD is that you just have too many measurements that do not fit in memory, so you cannot really do anything else than that. No? So that's also one of the cases where one wants to use that. So in concluding, Toro is an efficient maximum likelihood estimation algorithm for both 2D and 3D postgraphs. That it is robust to initial configuration. It's based on stochastic gradient descent, so it takes one measurement at the time and then compute the gradient for the whole state space just based on this measurement. And it scales up to millions of measurements, and it's also available open source on OpenSlam. You have two papers on the webpage that describe both approaches. The first one from Ed Olson on the incremental parametrization, and the second one from Giorgio Grisetti on the nonlinear version with the tree parametrization and the nonlinear update rule. That will be it for today. Do you have any question? Okay, so if there is no question, we'll see each other next week with the last lecture.